All right, let's start finite sets. So first we define the finite set, and since we already have the definition of the section, oh, yeah, since we already have the definition of the section, a finite set is a set which has a bijective correspondence with a section. That's about it. And then the book shows the first lemma, which is if I'm just going to write this for a bijection. So if there exists if A, this is the first lemma, right? Yeah. Now this lemma is useful because this will serve as the the thing we use in the induction step for the general case, which is the next one. So yeah, what it does is just swap around, and yeah, the proof is you should just read it. I guess it's pretty good. Okay. Now given this lemma, so yeah, that symbol is that backwards arrow is the symbol for a bijection here. Yeah. Okay. So first lemma here, and pretty much the only lemma. Yeah, this is proved by induction. And if B is a proper subset of A, right, then and A happens to have a bijection with N, so it has cardinality N by definition, right? Then what does the lemma say? Yeah, there exists no bijection uh, from B to this thing, and if B is not equal to the empty set, then there exists an M less than N such that there exists a G, B, yeah. Okay. And the proof of this lemma lies in essentially using the induction, right? So if it's true for one because the only proper subset is empty, and the empty set doesn't have a bijection with one because you can't. The empty set will give rise to the empty function, so it's not bijective if the other set is a non-empty, right? Now, if it's more than one, then we use the statement for the previous case, and to get from n to n plus one, we use the lemma, right? And from that, we get this big theorem, and this is the only useful theorem about for the entire chapter section. So with this theorem, we have a few corollaries, and I'll try to use them, prove them. Yeah. So if A is finite, um, I'm going to write this as the notation for A is finite. Will Some people already know what this means, but yeah, or this, I guess. Okay, this is what it means to be finite, right? By notation. Okay, so if A is finite, then yeah, what is it? The thing? Yeah. So if suppose that there is a bijection of A with a proper subset of itself, then by lemma there's a bijection between well, yeah, it contradicts. It's not possible because the theorem shows that. Hang on. Yeah, okay. We got a bijection between this and B, which is a contradiction. So yeah, it's me to assume the contradictory statement and then make the bijection. I mean, all the proofs are in the book, nothing much to add here. Z plus is not finite. That's one proof of it. Any other proof? I am not sure. Cardinality is unique because otherwise we have a bijection from n, section n to a subset of itself. This is a proper subset because since m is strictly less than n, there exists a subset. So the n itself is a member that's in this set and not in this set. So yeah, it's a proper subset. And it contradicts the lemma again, or theorem. So cardinality of B is less than A by the whole thing, by definition, and any subset of a finite set is finite. Yeah. And the last two theorems are also quite important. So we have three big theorems, and that's about it. So the following are equivalent. This, there exists G uh, on 2B. There exists G B into, no, 1, 1, Sn plus 1, right? Yeah. So bijections are by definition surjective, so we're done. For this one, surjective functions are, well, how does it do it? Hang on. I'm cheating. Oh yeah, that trick. This trick is quite useful. Okay, so because it's surjective, then G inverse B is non-empty. That's pretty cool. And because we have a function here, it's a rule of assignment, and because of that, G inverse P and G inverse P prime are disjoint. Because otherwise, what? Otherwise, B is equal to B prime. That's the only case where this can not be disjoint. So they're either disjoint or equal. This comes from the equivalence class thing. Yeah, and then it uses the fact that we're working with integers to define. Sorry, it's for the F inverse the whole time, but doesn't matter much. So f of B is equal to the least member of G inverse. So yeah, and the least member exists by the well-ordering properties. That's nice. Yeah, this trick is used in integers. This only works with integers. That's the key part here. Okay, for the last one, yeah, so if it's 1, 1, then you just limit the range and then you'll get a, yeah, so you'll get a bijection with a proper subset. And since, yeah, the last corollary is important before this one. So B is 1, 1 to Sn plus 1, right? Now, so how do we, okay, yeah, so all Sn plus 1s are finite. Observe that, right? And yeah, so any proper subset of S1 is also finite. And B is in a bijective correspondence with a proper subset of Sn plus 1. So it's a bijective in a bijective correspondence with something that's finite. And since bijections can be composed, you got a bijective correspondence with the section again by definition of finiteness. That's one way of saying it, or you can just directly use the corollary. Yeah, if B is a subset of a finite setting. Yeah, you're going to have to use that, I think. So that also works. Yeah. Again, the book pretty much covers it. There's nothing much for me to add here. Yeah. Okay. Yes. And the trick for finite unions and finite Cartesian products are so first for the inductive step, you show that A union B is finite. And for that, you first if B is finite, then we have either B is the empty set, which is trivial. And if it's not, then we fix bijections from what? So every finite set has a unique cardinality. Why? Because if it doesn't, by definition, right? So it has a cardinality by the definition of finiteness, and it has a unique cardinality by the theorem. So yeah, let's assume there's a map from Sn plus 1 to A and Sm plus 1 to B. And for A union B, yeah, we just define whether it won't be 1 1, will it? Hang on. Oh yeah, it's not 1 1, but we don't care. The point is it's surjective if we add the two maps together. So it just defines Sm plus n plus 1 to A union B. And the point is that this is a surjective map, which implies it's a finite map since it's equivalent. So that's what it's using and cheating very blatantly here, but yeah. Okay. So for finite union, you just use induction essentially, and you're going to use induction a lot here. In this case, we have A to an minus 1, which is a set A, and we have A n, and that's equal to the whole thing. So this is how we get the inductive step. And for that, we have the lemma of A union B, right? Yeah. Now, for Cartesian products, you observe that there's always a bijective correspondence between A cross B and B. And that's simply the map A comma B goes to B, right? Yeah. Because of that, we have a set that's finite, and since A is finite, A is equal to the finite union of the set. A cross B is the finite union of A cross B, and therefore is finite. Pretty good trick. Yeah. And that ends the theory portion. So to summarize, the useful things from this chapter is that you have to use induction to prove many claims about finite things, and you need that big theorem about what is equivalent. So if you have a surjective or an injective function, that's usually what you need to prove finiteness, not the bijective ones. Uh, and yeah, the well-ordering property was just a proof trick, and the subset one is just if you really want to go into the hard, but over the long term, that's not going to be the most useful theorem. The most useful one is what's solving our equivalent criteria, right?